In order to explain SVMs, let's see an example, where we try to classify 10 children based on their height and weight into boys and girls. With blue dots, we will note the data that corresponds to boys, and with red squares, the data belonging to girls. We can also label them using numbers and make our life easier later on. Therefore, let's say +1 will represent the boys, or the positive class, and -1 will represent the girls, or the negative class. SVMs in general try to classify data in a linear fashion, more specifically using a line if it's a two-dimensional problem, as it's here, or by using a hyperplane for high-dimension problems. A two-dimensional problem essentially means a problem where data is described by two features. So, in our example, the two features are the height and weight of each child respectively. So, let's focus on our example. Here we can see one possible solution, where a line can successfully separate the boys from girls. Is this the only solution? No. As we can imagine, there is an infinite number of lines that can do the same job. But then, which line provides the best solution? L1, for example, is unnecessarily awfully close to the data points, and that's not desirable, because it makes our model less general. This essentially means that if a new sample occurs which is slightly off from the two already established class, an example here is the orange triangle, we can see that the decision line L1 classifies the point to the boys class, where it's obvious to us that this point is significantly more similar to the girls. On the other hand, L2, which increases the distance between the two classes and consequently produces a more general model, can accurately classify the new data point to the correct class. In other words, we don't want our model to be trained just in a way to produce a correct result only for the given training dataset, but instead we want to make it in such a way that samples that are similar but not identical will be also correctly classified. Here we can see the best decision line for this specific problem, the line that is able to separate our data with the maximum possible distance between the two classes. The points with the black solid borders are the support vectors, that basically represent the points on the dotted lines, which are the boundaries. With knowing just the support vectors, we can uniquely define the decision line, and therefore, if we remove one of the support vectors, it is possible that the decision line could change. But if we remove any other point which is not support vector, then the decision line, or hyperplane, if we are talking for a higher dimension problem, will remain the same. You can imagine then that support vectors are extremely important for training our model. Now, as we already mentioned, our goal is to maximize the margin between the two classes. Before moving on, it would be useful to remember some different ways to define a line. One way to define a line is shown here. All the points that belong to this line must satisfy this equation. We can also rewrite the equation as shown below. Finally, we can write the same formula using now vectors, which will be helpful in a while. Furthermore, if we have a new point, we can describe it by its height and weight, or as a vector. It's just two different ways of defining or visualizing a point. Let's see now the decision rule that will help us separate our data. For example, let's say that we want to classify the new point U. Namely, we want to check if U is above the separating line or not. If we could take the projection of U over a line that's perpendicular to the decision line, then we could just check if the length of this projection is bigger than a specific constant which corresponds to the decision line. Therefore, we take a vector W which is normal. This means basically that it's perpendicular to our decision line. Then, in order to calculate the projection, we can simply calculate the dot product of the two vectors, like so, or equivalently like this. If a sample now satisfies this equation, then it's a positive sample, meaning that it belongs to boys. We have to keep in mind this equation because we will use it quite soon. Now let's try to find the equations that describe the lines in the boundaries, where the support vectors exist. Okay, so these equations describe the lines, but let's also write in a more general fashion the corresponding inequations for all data. More specifically, all data in the blue area must satisfy the following equation. Respectively, for all data in the red area, the following equation must be satisfied. We will try now to squeeze these two equations in one. Therefore, we have to define a new variable, y of I, that represents the target of each point. basically the label of the corresponding class for this sample. So, y of I is +1 for all positive samples, namely the boys, and -1 for all negative samples, namely the girls. We then multiply the equations with y of I and we get the following. Finally, we can take it one step further, because all samples satisfy the inequality, but for the support vectors specifically, a stronger constraint applies, and the inequality becomes equality. We keep also these equations for further use later on. Having all the previous information, we can try finally to find the form to describe the margin, which we want eventually to maximize. We can take two support vectors, one from each class. The difference of these two vectors can be seen here. The margin can be described as the projection of the aforementioned difference on the unit vector that is perpendicular to the decision line. But we have already defined W as a perpendicular vector to the line. So we can use the normalized W, which is the vector W over its magnitude. To calculate the projection, we need to take the dot product. Using now the distributive property for the dot product, we have the following. By using also the equation 2 from the previous step, we can finally calculate the width as 2 over the magnitude of W. This width is what we essentially want to maximize, which is equivalent to minimize the magnitude of W. This in turn is equivalent to minimizing the half of the magnitude of W squared. The only reason that we do the last is because it is mathematically convenient later on when we will calculate the derivatives. Basically, it is a constraint optimization problem where we want to maximize the margin or equivalently minimizing the aforementioned term, given the constraints that we introduced in the previous steps. We can take it one step further to see a powerful property that will be extremely useful when we will talk about kernels. So, by using the Lagrange multiplier method, we can rewrite the problem as following, where now our goal is to minimize the function L. We know that for the extremes, the derivatives are 0. Combining now the equation 3 and 4, we have the following. B here is a constant, so we can drag it in front of the summation, and from the equation 5 this term is 0. With a little bit more manipulation, we can rewrite the equation as so. Now we can see that the equation depends only on the dot product. Similarly, for the decision rule that we saw earlier, we can use the equation 4 in order to rewrite it and see that it also depends on the dot product. The important realization here is that neither the L equation nor the decision rule need the knowledge of x of i's, but they only need the knowledge of the dot product between the samples. This is extremely useful in the next step where we will discuss about kernels. As we already mentioned, SVM tries to separate data in a linear fashion. So how can we use it for non-linearly separable problems? We can transform our data and map them to higher dimension, where they will be linearly separable now. This probably sounds much more complicated than what it really is. So let's try to explain it through a simple example. Here we have a one-dimension problem that it is impossible to solve linearly, meaning that we can't separate the blue dots from the red squares by using a line. But if we add one more dimension, one more feature to the data, and specifically we can take as a second feature the square value of the first for each data point, then we can see that it's possible now to use a line to separate the two classes. But in order to transform the data, we need to know the transformation, which is not always easy, and for example, sometimes there can be an infinite number of dimensions. So how can we do it? As I told you previously, we don't need to know the transformation, but only the dot product between the transformed samples. And for this we use the kernels. Kernels are basically functions that take as an input the original samples and give us the dot product of the transformed ones. Here are some useful kernels: the linear, polynomial, radial or Gaussian, and the sigmoid. Unfortunately, there isn't a rule for deciding which kernel is the most appropriate for each problem. So, whoever is responsible to design the classification model must decide depending on the data that he has and probably sensitivity analysis is needed to determine the proper kernel and the best parameter values. Finally, we have to mention that SVMs natively can classify only binary problems. So, if we want to use them for a multi-class classification problem, we can use either 1VS-REST or 1VS1 methodologies. Let's see first the 1VS-REST methodology, where for each class we train a separate classifier that considers this class as the positive and the rest combined as the negative class. Therefore, for a problem with n classes, we need to train n classifiers. Now, if we want to classify a new sample, then each classifier makes a prediction with a given probability that the test sample belongs to its positive class, and the final decision is based on the classifier with the highest probability. On the other hand, for the 1VS1 methodology, for the same problem, we need n½ by n-1 classifiers. In other words, there will be one classifier per pair of classes. This way, each of the aforementioned classifier assigns any new test sample to one of the two classes that it contains. So, for a given test sample, there will be in total n½ by n-1 predictions, each originating from a different classifier. For the final decision, the class with the most votes is selected.